Hello, everyone. Mr. Minnick's my name. Math is my game. Today, my second period Algebra 2 class is going to bear witness to this informative, educational, continual lesson, continuation of what we talked about yesterday. Yesterday, we introduced exponential functions. We looked at a few graphs. We examined the graphs. We saw if the graphs increased or decreased. We talked about exponential growth, exponential decay. We talked about two different forms of the function. We talked about restrictions on the variables. And today we're going to continue with that talk. So the form y equals f of x equals a times b to the x. The big thing to take away from that is the b value. You really need to focus on the b value. To quote Ed Bassmaster, would you just look at it? Would you look at it? The b value, you really need to look at the b value. The b value is the number whose power is a variable. Okay, it's not always necessarily going to be x, but the b value ends up being a number whose power is a variable. Okay. The number 1 is real important because if the b value is bigger than 1, we have exponential growth. If the b value is between 1 and 0, we have exponential decay. The restrictions, you can check all that out on your own time. We looked at examples of the graph. We saw if there's growth or decay. We saw the y-intercept. We made conclusions. And we talked about Ashton-Kutcher. We said this has nothing to do with Ashton-Kutcher and Tyra Banks. But we did look at this form of the equation, and we'll come back to that. And then we talked about the b value equaling 1 plus r in the case of growth, or 1 minus r in the case of decay. So here's something new to add to your notes. The b value is also called the growth factor. Now sometimes it's the decay factor, so it's the growth and or the decay, well not and, but it's the growth or decay factor. So in the exercises tonight, they might tell you to identify the growth factor. They might ask you to identify the decay factor. All that is the b value. Okay. The growth or decay factor is the b value. A lot of textbooks like to use that particular language. So the b value is called the growth factor or the decay factor. So we're going to be coming back to this page because we're going to look at some application problems of both of these. We talked about the initial amount. It's when time equals 0 when we first begin the model. We looked at an example. We talked about a lizard, Starvin' Marvin, if I remember right. Starvin' Marvin started off with 36 mealworms. And then we looked at a graph, and we said that the graph isn't funny, but it does have a horizontal asymptote, and we'll talk more about that in our second example. And then the last thing we ended up with is how to find the growth and decay rate. So our first example is going to follow directly from this. So that should be the last thing in your copious notes if you took them yesterday. And at this time, I'd like to give a shout out to my 6th period class because they're watching both parts of this video. So a shout out to Taylor Mate, Gage Armstrong, Evan Penna, district champ in the 100-meter dash. The future Mr. Minnick probably sitting in the back grading papers or taking copious notes. All right, so here we are. Example number 1. Determine whether each model represents exponential growth or exponential decay. Also, give or state the rate of growth or the rate of decay. So I'll give you a minute to jot down those directions. And we're going to look at least 4, maybe 5 or 6 of these, however many it takes to get the idea across. Just a friendly reminder, there will be, for any student who's not a senior, there will be a quiz on Tuesday over this material. And the first 5 questions on Tuesday's quiz are going to be the exact same format as this first example. So, part A, let's look at this equation. Y equals 0.7 times 1.4 to the xth power. So whenever I do these, to be safe, I think back to what I heard myself say a minute ago. You got to look at the b value. So maybe we should identify the b value. What is our b value in this particular instance? 1.4 is to the x is our b and then the x. So the b value is just this 1.4, right? So let's back that thing up for a minute. What did we say? We said that the function represents exponential growth whenever the b value is greater than 1. Well, there it is. So what is the answer to the first part of this question then? Is this growth or decay? Growth, good. Does everybody get that? Okay. So this is or represents exponential growth. So the other part of this, the and then part, is what is the rate of growth? And to find the rate of growth, I strongly urge you to look at this formula. To use it, 100 times b minus 1%. 100 times b minus 1%. So let's try that. 100 times b minus 1%. So that's 100 times b, times 1.4 minus 1%. Anybody able to do that math and see what we get for our growth rate then? %. Nice, good. Can I shout you out? Shout out to Tucker, brought his A game today. And another shout out to Gage. Good. All right. How do we feel about that first example? Okay. All right. Let's try another one. Example 1, part B. Y equals 1.4 times 0.7 to the x. And you're going to say to yourself, these are the same numbers. Well, yeah, they are. But they're in different places. What's our b value in this one? Our b value here is 0.7. So we know that if the b value is bigger than 1, we have growth. Well, okay, but what happens if the b value is smaller than 1 but bigger than 0? What do we have here? Decay, good. So this is exponential decay. Now, if you want to find the rate of decay, some people are just going to look at that, and they're going to say, well, it's 70%. I got news for you. You're wrong. My advanced class, when they took this quiz, the ones that missed this, they bombed the crap out of this. They had no idea what they were doing. So let's back that thing up. The rate of decay is 100 times 1 minus b, and you're looking at these two things, and you're saying, dude, they're the same thing. No, they're not. Subtraction is not commutative. It never has been, and it never will be. So for the rate of decay, it's 100 times 1 minus b. It's 100 times 1 minus b. So let's see how that goes. 100 times 1 minus b %. 100 times 1 minus 0.7%. So let's do the math and see what we get there. Somebody said it? 30%. Good. So the decay rate here is 30%. Okay. I don't know why, but a lot of people struggle with finding the rate of decay more so than the rate of increase. We doing okay so far? The next example I like to use is called a doubling function. It's perhaps my favorite thing. You can really confuse somebody with this. It's called a doubling function. It's probably no surprise that this is exponential growth or represents exponential growth. What will surprise you is when you think about this statement. If something is said to double, its rate of increase is what percent? If something doubles, its rate of increase is 100%. 100%. A lot of times when we hear the word double, we want to think 2, and your gut instinct says it's 200%. It's not 200%. If you follow that formula, it's 100 times b minus 1%. So it's 100 times 2 minus 1%. So when something doubles, its rate of increase is 100%. When something triples, its rate of increase is 200%. When something quadruples, its rate of increase is 300%. You picking up what I'm putting down? Okay. All right. Let's look at another one. Number D, y equals 8 to the negative x. I would be amazed. I would be overwhelmingly joyed if someone could tell me the b value of this. This is kind of like a transformer. Robots in disguise. More than meets the eye. You know. Anybody got the b value, they think? What are you thinking? 8's a good try, but the b value is not 8. It's not negative 8 either. Negative exponents have never, nor will they ever, make a number negative. 1/8 is what it is. Good, good. It's 1/8. The b value here is 1/8. If you're not sure how that comes to be, what somebody cleverly did here is they said, well, this is 8 to the negative first to the x. Remember your power of a power rule? And 8 to the negative first becomes 1/8, so it's 1/8 to the x, so your b value is 1/8. Okay. I don't like to throw those at you. I think they're confusing. But if you take a college math class, they're going to litter their tests, their homeworks, their quizzes with that. I don't know why, but they like to. So so this is clearly then decay. Well, be consistent. I'll go ahead and use red. Red. Decay. And anybody got the rate here? I'll let you figure it out later on. It's 87.5%. 87.5%. Okay. So that's decaying pretty rapidly, pretty quickly. How do we feel about identifying something as representing growth or decay and finding the rate? Do we feel like we've had enough instances of that to get the idea? Okay. So like I said, Tuesday's quiz, the first 5 questions will be the exact same format, different numbers, but same format, same expectation of you. Okay. Moving right along then to example 2, I'd like to try to have some kind of growth scenario. I'd like to use a population too. In my other class, my first period class, we didn't talk about animate objects. So I'd like to talk about animate objects for a second. And I am going to go on the record and say this. Animate objects. What I mean by that is something that has a heartbeat and a brain. So a snake, a cricket, a dove, a person, a bear, a frog, a duck-bill platypus. Okay, animate objects use chop-off rounding. This is my preference. Whenever you have a class with another teacher, please ask them their preference. Some people believe that 7.1 snakes, if the snake has its head and that head could harm you, that you have 8 snakes. I don't believe that. I believe if you have 7.1 snakes, you have 7 entire snakes, and that's it. So I'm saying anytime you have an animate object, if there's a decimal amount, just chop it off and use chop-off rounding. Does that make sense? That's my preference. So that being said, the population of mongers, I'm just making something up here, was 300,000 in 1975. The population of mongers has steadily increased at a rate of 1.9% since 1.9% per year, 1.9% per year since then. So we're going to do a couple things with this. We're going to write a model. We're going to see how many mongers there are now, and we're going to see when the population of mongers is going to be 5 million. I don't know what a monger is. I just made the word up. Okay. So part A, write a model. Write a model. Part B, how many are there now? How many mongers are there now? And in part C, when is the monger population going to be 5 million? That sounds pretty intimidating. 5 million mongers. Doesn't it? Sir, could you please stay off your phone? It's very distracting to me. You too. Write a model. How many are there now? When is the monger population going to be 5 million? And I forgot my question mark. Question mark. Cool. All right, so when we want to write a model, we could look at the forms, but the second form I gave you, that's the one we're going to use here. This a of t equals a sub 0 times 1 plus r to the t. When we're talking about growth, we're going to use 1 plus r. We're talking about these mongers increasing steadily in number. So we're going to use this form. So we'll go ahead and write, if I could find it, here it is. We're going to write a of t, the amount of mongers after so many years, is going to equal. Now I need my a sub 0. That's the starting amount. That's how many I had in the beginning. How many mongers were there in the beginning? 300,000. So that's going to be going right here, 300,000. Okay, times 1. Well, I'm going to leave that blank for a second. I'm going to go ahead and do a thought bubble and think to myself, self, what do I know about my b value? My b value for growth is 1 plus r, right? Well, what's the rate? 1.9%. What did your algebra teacher teach you that you have to do with a percent anytime you're working with an equation? Anytime you're working with an equation, what do you have to do to a percent? You have to change it to a decimal. So 1.9% is 0.019 as a decimal, right? So my b value here is going to be 1 plus 0.019. So my b value here is 1.019. My advanced class, when they took their test, half of them bombed it. And you know why they bombed it? Because they screwed up their b value. If you screw up the b value, you have no chance of getting this right. No chance. The number 2 spot where people make mistakes on this is what they use for their exponent. Okay? People want to plug in 43 when they write their model. Do you know where 43 comes from? Let's think about it. It's 2018, right? So it's been 43 years from 1975 to now, because it's talking about the rate per year. But when I write the model, remember when you write an equation, y's are y's and x's are x's, right? So when you write a model, what I'm getting at is the exponent's got to stay as the variable when you write your model. When you do the next part, you are going to plug in a 43 and see what happens. And I hope you have your calculators, because you're going to need them right about now. So the amount of mongers right now, the amount after 43 years has passed, is going to be 300,000, my bad. 300,000 times 1.019 to the 43rd power. And remember, we want to use the chop-off rounding method. So my Inspire probably doesn't play well with my smartboard, but I'm going to give it a go. 300,000 times 1.019 to the 43rd power. So, are there a million of these things yet? No. 673,924. We're chopping off. 673,924. 673,924. Okay. So part C, trying to solve that, is why I love the TI Inspire. The TI Inspire does this better than any calculator I've ever seen. For part C, we could write an equation if we want to. Maybe we do. We'll say 5 million equals 300,000 times 1.019 to the t. Now we could divide both sides by 300,000, or we could just guess and check. Maybe we could just plug this in, and after 43 years that happened. Let's see what happens after 200 years. After 200 years, we end up with 12 million. So it's not going to take that long. So what's another number we might want to try? 100? Okay. 100 gets us to 1,000,009. 150. This is like rabbit hunting with statisticians. Wow, that's close. 148. There's a better way. I think Kurt Cobain said it. Got to find a way, a better way, a wetter bay. On the Nevermind album, anybody ever hear that song? Anyway, do you guys ever hear of this feature that the calculator has? Remember that? Oh, you mean you can use this with big numbers? Sure you can. And solve 5 million equals 3 1 2 3 4 5 300,000 times 1.019 to the t, and I want to solve this for t, and it's going to be 149 and a half years after 1975. So I guess we'll take that and add it to 1975. And so in the year 2124, there will be 5 million mongers, assuming the model continues. That's a pretty big assumption, because the world is supposed to end 17 more times between now and then, because the Mayan calendar is going to run out, right? Okay. Does everybody get the idea here? So this is about 149 and a half years after 1975. So sometime in the year, what do we say, 2021, 24? In the year 2124. Okay. I need to take a break before we start the next segment, because it has some information that I got to be honest with you. It's pretty grave information. Let me look that word up while I'm preparing myself for this next one. What's a good reference for dictionaries? Dictionary.com or Webster? Or Webster? Okay, well, let's go to Webster. Webster. Merriam-Webster. So the word grave, in the context that I used it, I'm not talking about this carved or shape with a chisel. And I'm not talking about excavating either. And I'm not talking about cleaning and paying with pitch. I'm using it in this context. This is meriting serious consideration, likely to produce great harm or danger, significantly serious. We're going to talk about the human body for a minute. Okay. So example 3, an application problem. Your kidneys, dyslexia strikes again. Your kidneys can eliminate substances at a rate of 29% per hour. Your kidneys are very good at what they do. And so you should be good to them. But anyway, that's another story. Suppose you ingest 2,000 milligrams of a substance at midnight Saturday and have a job interview / drug test 09:30 Monday morning. The test center, can test to 1 ppb. Here's the question. Do you pass? Very real scenario. You're at a party Saturday night. Somebody says, here, take 2 of these. I found them in my mom's medicine cabinet. Narcos, Vicodin 3s, Tylenol, ENs or ESs or whatever the ones people are prescribed nowadays. You know the number one thing that employers tell me? They say, we can't find people that want to show up for work. And when we do, we can't find people who can pass a drug test. This stuff happens every day. If you don't think it does, I'm not going to tell you what choices to make in life. I'm going to show you math. That's a real number that medicine has determined your kidneys can do. Have you ever watched the show CSI? They have their little Geiger counters and they talk about ppb. That's a unit of measure. Does anybody know what ppb stands for? ppb stands for this. It stands for parts per billion. Parts per billion. So that's 1 divided by a billion. That's 1 times 10 to the negative 9th power. So that's 0.000000001. So we need to try to come up with a number smaller than that. Okay? So we'll write the model in a second. But let's think about the math, the numbers, what we're going to plug into the model. Well, I guess we'll write the model. The amount of a substance in your bloodstream after so many hours is going to be 2,000 times. Anybody got the B value figured out yet? It's 1 minus R. So it's going to be 1 minus 0.29. So it's going to be 0.71. Okay. So there's our model. Let's do the math, though. Let's think. From Saturday midnight to Sunday midnight's 24 hours, right? Sunday midnight to 9:30 is another 9.5. 24 and 9.5 is going to put us at 33.5 hours, right? So let's start plugging some stuff in and see what happens. Let's see how we do. Monday morning, taking this test, 2,000 times 0.71 to the 33.5. We have 0.02 of a milligram in our bloodstream. Is that going to show up? You better believe it is. Well, we could take a masking agent. Oh, but wait, they test for those too. Well, I'll just drink a bunch of water. Well, they'll test other things and they'll know you drank a bunch of water too. So let's go a day later. What's 24 more hours? What if you call in sick to your job interview? Oh, I'm sick. I can't come in for my job interview. Let's just run with it. Suppose that they did. Suppose that they bought your cock and bull story that you were sick for your job interview, and they gave it to you the next day. 24 hours after 33, what's that going to be? Thank you. So 2 days later. Now remember, we're down to parts per billion. We need to be smaller than 1 times 10 to the negative 9th. Are you going to pass now? Okay, let's say your grandma died, and you had to be there for your... I'm sorry, I know that's probably insensitive, and I don't mean it to be insensitive, but suppose you got a funeral slip, and you legitimately went in on Wednesday. So let's go 24 more hours. That's going to be 81.5, right? It's got to be smaller than 1 times 10 to the negative ninth, is it? I'm not telling you what to do with your lives. I'm telling you how math works. Last thing we need to talk about today is the compound interest formula. It goes like this. A equals P times 1 plus R divided by N to the N times T power. Probably the second scariest formula you'll ever see in a math class. Maybe first would be the quadratic formula. I think is worse than this. I think it's not as bad. Well, I don't know. This is a pretty bad one though. So A is the amount of money in an account. So maybe you were gifted $1,000 and you don't want to blow it. So you go to the bank and you're like, bank, I know if I put my money in you, you'll make money for me. That's how banks work. So P is spelled just like Ms. Kizabeth. It's principal. Principal. It's the investment amount. It's the investment amount. It's how much money you're going to take to the bank and deposit in there on day one. R, probably not a surprise. R is the interest rate. It will be given as a percent. Remember, you're going to have to convert it to a decimal when you use it in here. T is time in years. T stands for time in years. Unless otherwise specified, it's always going to be in years. So I gave this quiz to my advanced class last week, and many of them bombed it. They bombed the second part because they got their B value wrong. They bombed this part because they didn't jot down what N is. N is the number of times per year interest is compounded. There's a formula called simple interest, and there's a formula called compound interest, and this is the compound interest formula. What it means is the bank's going to say, you know what? At the end of every year, we're going to run an algorithm, and we'll let your money earn money. At the end of every day, we'll run an algorithm. We'll let your money earn money. Or maybe they'll say at the end of every month, we'll do that. So the deal is, if the interest is compounded annually, your end value is going to equal one thing. If it's compounded semi-annually, the end value is going to equal something different. If the interest is compounded monthly, the end value is going to be something different. If the interest is compounded every 3 months or every quarter of a year, that's something that in business they really talk about. You ever hear of somebody saying they're going to their quarterly report for the business or to the quarterly meeting? The end's going to equal something else. And if the interest is compounded daily, the end value is going to equal something else. So what's n going to equal if it's annually? How many annuals are in a year? 1. What about semi-annually? 2. Monthly? 12. Quarterly? 4. And daily? 365. And don't say 360. Well, you couldn't say 366 in a leap year, but for all these problems, we never worry about leap years. Never worry about a leap year. Okay? So the last thing we need to do today then is use this formula, and we'll be done. I'd like to give a shout out to middle school for being such a fun time. I had such a good time in middle school. Anybody else? I remember running down the hallways and jumping up and touching the ceiling and signing my name, Air Minnick, on everything. That was a good time. Example. Jane deposits $2,000. Well, we'll make it $1,000. Jane deposits $1,000 into an IRA that accrues at a rate of 5% per year. How much is, or will it be, worth after 20 years, if interest is compounded in the following ways. Part A, annually. Part B, monthly. Part C, daily. I'd really like to do a part D here, because suppose somebody's a hacker. And suppose that they could somehow, some way make interest compounded every second. Okay. So you're going to need to use the compound interest formula here. When you do these problems on Tuesday's quiz, if you don't show work, if you don't show what formula you used, and you get the answer wrong, even if you're off by a penny, I am taking off all the points. If you don't show your work. If you show your work and you're off by a penny, I'm still taking off a point, because that's how precise you got to be. You got to be within 1/100th. You got to be dead on. So the formula is A equals P times 1 plus R divided by N to the N times T power. So for part A, we're going to go ahead and say that A is equal to our principal, our initial value, our initial investment amount, 1,000, times the quantity 1 plus R. So what's that? 5%, which is going to be 0.05. If you screw up your R in this, you're going to be way off. So make sure you get the R right on this. Divided by N. What's my N for annually? 1. Raised to the N times T power. So to the 1 times, what do I use for T here? 20. Good. So you can punch that in on your calculator. And I hope everybody can come up with the same dollar amount, because Tuesday's quiz, there's going to be 5 of these. So see if you can punch that in. We want this all the way down to two decimal places, to the nearest cent. Just an idea, your answer's going to be bigger than 1,000. People screw this up all the time. They get like $1,005. It's going to be bigger than 1,000. Some people get $1 trillion. You're not going to put $1,000 into the bank and end up with $1 trillion 20 years later. Okay, your answer, it might double, maybe it'll even triple, but it's not going to be in the billions or millions. Anybody got it? What do we got? There it is, $2,653, and I heard a 0.3, so 2653. Need a dollar sign, 2653. Now, when you go to Walmart, the price tags don't say 5.9, do they? They say like 5.99 or so. So it's 2653, and then it's 0.297. You got to use your standard rules of rounding for money. That's going to round to how many cents? To 30 cents. So 2653.30. Okay, I will require you to be that precise. Monthly. The cool thing is your calculator, you could just copy paste on the calculator. The only thing that's going to change is your N. What's your N going to be here? 12. Good. So that's to the 12 times, that's to the 12 times 20. So on your calculator, you can just scroll up to the last entry, press enter, copy paste, and change those 1s to 12s. And you should get 2712.64. Got it? $2,712.64. So for daily, the only thing different for daily is what's our end value going to be? 365. So this is going to be 1,000 times 1 plus 0.05 over 365 to the 365 times 20. On the quiz, I don't need you to write this all 3 times, but at least tell me what you're using for N on the second one and on the third one. Does that make sense? Okay. On the second and third one, you could just write n equals instead of having to rewrite the whole thing. Absolutely. Absolutely. But I do need to see that formula that's used for the first one in that string of problems. So this is what, 27, 18, 10? 27, 18, 10? Is that what you guys got? If you're not coming up with these, you got between now and Tuesday to figure out how to. So be sure that you're comfortable doing that on the calculator. Now, the movie Rent, probably one of the had one of the catchiest songs I've ever heard. 525,600 minutes. Wasn't it? Let's think about this. Every second, there's 525,600 seconds in a year. Wow. Is that right? 365 days, 24 hours in a day, 60 minutes in an hour. Oh no, that's how many minutes. That's every minute. We got to multiply that by 60. Oh man. Dude, this is huge. 31 million. 31 million 536,000. So, if we compound interest every second, surely this number is going to be huge, isn't it? It might surprise you. And the hackers in this context maybe don't know as much math as they think they do. I don't even know if I can plug that number in. I know what I'm going to use. I'm going to use the ANS on my calculator. I'm going to use the little ANS feature. Okay, so it ends up being 27, 18, 30. Wow. 27, 18, 30. At some point, what ends up happening is you're probably thinking, well, wait a minute, this is getting huge. Yeah, and so is this. But the deal is, even though this is getting huge, this is getting big too. And so this whole fraction ends up becoming smaller and smaller and smaller to a higher power. So they kind of offset each other. And there's actually this gives birth to a new formula that hackers didn't know existed called the continuously compound interest formula. So we'll talk about that next time. It's been real. It's been fun. I hope everybody has the best day of their lives. See you next time.
Good.